Hello there, Mr. Sutton bringing you this lesson on Maclaurin series. In this one, we'll be constructing Maclaurin polynomials to approximate functions. That's the name of the game today. And we'll also find nth derivatives and coefficients of these polynomials. So at some point in your mathematical career, you may have wondered why we care about polynomials, and your teacher might have told you, well, they're function chameleons. They can be made to look like any other function. We're going to see that in action today. It turns out using information about a function and its derivatives at a single point, we can make a polynomial that simulates that function. To see this in action, go ahead and check out the behavior of a polynomial built to mimic the sine function in this Desmos link below here. And to do this, you just have to move the K slider around and watch the fun. So here's the screen that link should take you to, and I'm just going to press play on my K slider here. So I'm just adding more and more terms to this series, this polynomial series that simulates the sine function. And this is what happens to my blue function, my polynomial, as I add more and more terms. It looks like that it's more and more resembling the sine function that it was based off of. So just coming back to my presentation and taking a few snapshots for the highlights, at the very beginning with a low k value, our polynomial didn't really look that much like the sine function. But as k increased, the polynomial came to more and more resemble that sine function. And at some point at like k equals 18, you can't really even tell the difference anymore. I mean, there's a little piece where we're veering off at the very end, but it's hard to tell. So this is kind of the motivation for what we're doing today. Today, we're going to be figuring out how to build polynomials like this, just centered at x equals 0. Later on, we'll address the question of how can we build polynomials centered anywhere. And we'll also ask, if we're trying to approximate with one of these, how far off is our approximation? What's the error bound? And then finally, because these are polynomials and they veer off at some point, how far out can we go before our polynomial veers off into space? What is the interval of convergence? Just to name what we're actually doing today, we are building what are called Taylor series. A Taylor series is a polynomial built using the value and derivatives of a function at a single x value. Now we're focusing on a specific type of Taylor series today called a Maclaurin series. Maclaurin series is a Taylor series centered specifically at x equals 0. And these are actually a lot easier to work with than if you center it somewhere else. So to build these, we're going to use the formula for the nth term of a Maclaurin series, which is given by the nth derivative of 0 of some function over n factorial times x to the n power. Now, if you're wondering where that formula comes from, I did a little 10-minute origin story video that you can check out. However, knowing where it comes from isn't actually going to help you use it any better, so in this lesson, I'm focusing on how to use it. So let me write out the first few terms with some specific numbers for n. The first two won't make much sense, but then it'll start making sense. So the first term of your series using this formula is going to be just f of 0, followed by f prime of 0 times x. And again, I'll explain those in a minute. The next one, using a value of n equals 2, it's going to be the second derivative of 0 over 2 factorial times x squared. Then third derivative of 0 over 3 factorial x cubed. And you could keep going as far as you needed to. Now, if you're wondering about these first two terms, the 0th derivative of a function is just the function itself. X to the 0 is 1, so you're not going to see that. And 0 factorial is also actually 1. It's just the number of ways of choosing 0 items. This next one is just an n value of 1. First derivative, x to the first, 1 factorial. So this is, if you keep going, this is a series, but you might also see tell of a Taylor polynomial of order k, which they might symbolize as p sub k of x. And k is actually going to be a number like 3 or 4. What we're talking about here is just a polynomial that has all the terms up to the kth derivative. So it doesn't go forever. We're just stopping somewhere. For example, if I had p sub 2 of x, I would be essentially talking about these first three terms up to this second derivative here. Now, I want to be careful and really define this order thing as having to do with the derivative and not necessarily the power. In general, the order and degree of a polynomial will be the same unless your last derivative has a value of 0. Like if you had f, quadruple prime of 0 was actually 0, then you wouldn't see the x cubed, and then your degree would actually be one lower than your order. At this point, we're going to write the first four non-zero terms in general term for a Maclaurin series for ln of 1 plus x. Now, if you haven't already written out the Maclaurin formula somewhere else, I'm going to write it out here. I mean, you already wrote it before, but if you're just doing this somewhere else, I would write this out first. It's very helpful for figuring out where things go. Next, we have a bunch of derivatives we're going to need to find. They want the first four non-zero terms, so we're going to find enough derivatives to write that number of non-zero terms, which is to say, if we find a derivative that's 0, it doesn't count towards this minimum of 4. So we'll keep going until we get 4 non-zero derivatives. We also have to start with the original function, f of 0. So f of 0 here, that's just ln of 1 plus 0, just ln of 1. That's just 0. So that's not going to count towards our first 4 non-zero terms. First derivative, that's going to be 1 over 1 plus x, or 1 plus x to the negative 1, evaluated at 0 now. I'm just using my little evaluation shortcut here. That's just going to be 1 plus 0 to the negative 1, which is just going to be 1. Second derivative now, that's going to be negative 1 times all of this to the negative 2, evaluated at 0. That's just going to be negative 1. This parentheses term is always going to come out to 1 when you're plugging in 0. It's just what you get out here in front. So this is negative 1. So we've got 2 non-zero terms. Pause the video and take enough derivatives to get 2 more non-zero terms. All right, so hopefully you started with the third derivative. That's going to be 2 times all this to the negative third power. And evaluated at 0, that's just going to give us a value of 2. Fourth derivative, that's negative 6 times all this to the negative fourth. And with 0 plugged in for x, that just gives us negative 6. So count them up. We've got 1, 2, 3, 4 non-zero derivatives, which is going to give us the first 4 non-zero terms. Let's go ahead and plug things into my formula here. F of 0 was just 0, which I wouldn't typically write, but I'm being very descriptive in what's going on here. F prime of 0 we saw was just 1. So now we have 1x. And then f double prime of 0 we saw was negative 1. But be careful here, because in the formula you're always dividing by the factorial that matches the derivative number. So this is really negative 1 over 2 factorial times x squared. Next we've got 2 over 3 factorial x cubed. And then finally minus 6 over 4 factorial x to the fourth, and a bunch of other terms. And we're going to worry about our general term in just a moment. Sometimes if you can't see a pattern readily available, it helps to simplify and then use the pattern to write the general term. Looking at these terms here, I mean, obviously we have an n factorial down there and an x to the nth power, but I'm not really sure what the relationship is with this numerator just yet. So let me simplify these. F of x we can say is just x minus 1/2 x squared plus, well, 3 factorial is really 6. So this is going to be 1/3 x to the third. And over here, 4 factorial is really 24. That's 4 times 3 times 2 times 1. 6 over 24 is really 1/4. And in fact, if you really think about it, this is really 3 factorial over 4 factorial. So you cancel out everything except that first term in your factorial. So there is a pattern here. We've got x to the 1. We have 1 over 2 x to the 2, 1 over 3 x to the 3. So in general, this is going to be 1 over n x to the nth power, which is easier to see when you've written all that out. But there is one other thing going on here. We're alternating terms, so we're also going to need a negative 1 times n plus 1 to make this happen. Why is it going to be n plus 1? Well, if I have a first n value of 1, which I'm going to need so I'm not dividing by 0 right here, then I want the first thing to come out positive, so that would need to be 1 plus 1, even power on that negative 1 there. For this next problem, we're going to do something similar, but we're going to change things up a little bit. Here they want us to construct the third order Taylor polynomial at x equals 0. So remember, at x equals 0, they really just mean a Maclaurin series, but they want to go to the third order, so we're going to stop when we get to the third derivative. The function we're doing this time is e to the 2x, And when we get that polynomial, we're actually going to use it to approximate f of 0.8 on the calculator. But let's start by just getting third order Maclaurin series for f of x equals e to the 2x. Pause the video and see if you can build that series. Okay, so we need to start with f of 0. F of 0 here, that's e times 2 to the 0. That's just going to be e to the 0 or 1. Now we need f prime of 0. So f prime in general, that's going to be 2e to the 2x evaluated at 0. That's just, and now when you plug 0 into this e expression, that's always going to come out to 1. So it's just this number out in front that's going to be the deciding factor. So this is going to come out to 2 times 1 or 2. Second derivative, that's 4e to the 2x evaluated at 0. That's going to just come out to 4 if you plug in 0. Third derivative, we need third derivative because they said third order, so that tells you exactly how many derivatives. That's going to be 8e to the 2x evaluated at 0. And that's going to come out to 8. Building our polynomial now, because we have our three derivatives, we've got 1 plus, this is going to be 2x, plus this is going to be 4 over 2 factorial x to the second. And then we've got 8 over 3 factorial x to the third. So if you're not going to write out the general formula, just remember to divide by those factorials as you go. If you want, we could simplify this a little bit. So 1 plus 2x plus 2x squared plus this would be 8 over 6, so 4/3 x to the third. And at this point, we're going to go ahead and use this to approximate f of 0.8. So to do this, you just plug in 0.8 into this polynomial on your calculator. But you do need to be careful about your notation when you show this. When approximating a function with a finite Taylor series, so a truncated polynomial here, you must use the approximately equal symbol right away. So I'm going to write f of 0.8 is approximately equal to p sub 3 of 0.8. And now I'll actually plug that in. So I've entered my polynomial in my y equals. I'm just going to quit out of there and do alpha trace to pull up y1, plug in 0.8, and that's going to come out to about 4.563. And I'm just kind of curious how close this approximation was to the true value of f of 0.8. So let me figure that out. The true f function, which I'm just going to put in y2, was really e to the 2x. So getting out of there, let me do alpha trace and then do y2 of 0.8. And that comes out to about 4.953. So it wasn't too far off. I mean, it wasn't super close. But here's the thing. If you wanted to get closer, you could have done more terms. Another common problem type, instead of just writing out a whole series, is they might ask us to find the coefficient of one of the terms. For example, coefficient of x cubed in a Taylor series for sine of x about x equals 0. So Maclaurin series for sine of x. In this case, we're just going to use the non-x part of our Taylor formula. So coefficient is just going to be the nth derivative of 0 over n factorial. So we no longer need the x to the n piece of this. Specifically on this problem, since we're dealing with third power, we're going to say third derivative of 0 over 3 factorial. And to do this now, we just need 3 derivatives of this function. So go ahead and find the third derivative of sine at 0 and see if you can fill the rest of this out. So our first derivative is going to be cosine of x, and we don't need to know what that is at 0. We just need to know the third derivative at 0. Second derivative in general is negative sine of x. Third derivative, that would be negative cosine of x, but now we want to know the value at 0. So let's plug 0 into that. That's going to be negative 1. Now be careful here. For coefficients, don't forget to divide your derivative by the factorial. So this is going to be negative 1 over 3 factorial for the actual coefficient. For this next problem, they're giving us a Taylor polynomial for some function, and the first thing they want to know is the fifth derivative of this thing at 0. So the key here is that you have this general formula for what the coefficient should be, and you have actual coefficients to work with here. So what we're going to do is take the general formula for your coefficient at, this would be x to the fifth that we would want, and then just set that equal to the actual coefficient and solve for the derivative. So our x fifth coefficient ought to be fifth derivative of 0 over 5 factorial. That's what it ought to be. Now, what is the actual coefficient of x to the fifth in what they gave us here? Well, looking over here, this is going to be a negative 1 over 64. So we'll set those equal. And now we're just going to solve for the derivative piece that was in our coefficient formula. So to get the fifth derivative, I just need to multiply by 5 factorial. And we could call this done, because it doesn't have to be simplified. Or if you simplify it, this is really 120 over 64, ends up simplifying to negative 15 over 8. So one other cool thing that they could have us do is figure out whether this function has a local min, max, or neither at x equals 0. Because you need to know first and second derivatives in order to figure this out. Using the process we did over here, see if you can actually figure this out with the polynomial they gave you. All right, so my first step, I want to find f prime of 0 to see if I even have a critical value at 0. F prime is going to be the coefficient of x. I don't see an x term up here. So that means f prime of 0 must have a value of 0. So we at least have a critical value. For f double prime, I have my coefficient formula, f double prime of 0 over 2 factorial. That's what the coefficient of x squared ought to be. Now the actual coefficient of x squared up here is 1 over 8. So setting those equal and solving for f double prime of 0, I end up with 2 factorial over 8 for that second derivative. And I mean, that simplifies to 1/4. The important thing here, though, is that that is a positive number. Since I am concave up, and I'm at the bottom of that, that means that f has a local min at x equals 0. So this concludes our first look at Maclaurin series. Till next time, Mr. Sutton signing off.